Hope everyone had a good weekend. We're doing all right here, except the smoke has started to invade, so you can taste it in the air. It's pretty rough. Um, I've been really overwhelmed with a lot of administrative work. So a whole bunch of contractual language and formation of bar-chain publishing and a bunch of rev stuff to take care of. So I'm a little bit behind the gun on preparing slides. But what I will do is try to do some real-time work so that people can see what this is all about and try to give you the intuitions. So let me screen share. All right. So what I want to talk about over the next couple of Caspers is adding Clifford algebra to rholang, which will introduce Clifford algebras and at the same time start to talk about how you could apply OSLF to Clifford algebras. And so, of course, probably the first question that everyone has is, what's a Clifford algebra? So I was in the middle of kind of giving an example before defining it generically. I will recommend that, first of all, there's some great books. So David Hestenis has a good book on Clifford algebras, and then Doran and Lazenby have a book called Geometric Algebra, and both of those are good introductions. The Hestenis book is more axiomatic in nature, and the Doran and Lazenby is more focused on applications. And I also want to recommend that there are just tons and tons of Clifford algebra tutorials on YouTube. And many of them are quite clear and good. So like Mathoma, I think, has some good ones. And yeah, if you just do geometric algebra on YouTube or Clifford algebra on YouTube, you'll find tons and tons of presentations that will fill in any missing intuition. Essentially, the idea is that we're going to introduce some products. So if I let A and B range over elements of a Clifford algebra, then we'll be able to define a what's called the geometric product or the Clifford product. And we can see this as, if we think of these as like vectors, they're a little bit more sophisticated than vectors. There's more stuff going on. But if you think of them as like vectors, then we're going to get operations like this. And A, and I need to go find. Okay, so you can think of this as the inner product and this is the outer product. This is not the same as the cross product. You can use, and it turns out that this one, well, this one anti-commutes. And so using the anti-commutivity, you can derive these two from this one. So in particular, we have, hang on a second, I'm just gonna fix this up a little bit. There we go. You can get that A dot B is equal to 1/2 the geometric product. And you can get that a wedge B I like that one better. Why did it do that? Okay. So A wedge B is that. So you can think of the geometric product as more fundamental, and you can think of these as derived from the geometric product. But these identities are important to keep around. In general, if we're looking at, say, the Clifford algebra 3 space, then there we can sort of think of the generators as being 3 orthonormal vectors. So these guys are the usual, you know, they're all orthogonal to each other. So you notice that this thing is always a scalar, right? So you're, with this addition, you're allowed to mix types. So that's something that's we'll see a lot of. So think of this as a kind of formal sum, and this will kind of be your guide. So you have 3 orthonormal vectors. You have some a field of scalars, so like the real numbers. Then you have these things called bivectors, which are pairs of the orthonormal vectors, and you can think of them as describing areas together with an orientation. And then you have a trivector, which you can think of as an oriented volume. In general, if you have n of these, then you can kind of see how the pattern might go, and you'll end up with in, you know, the n space volume as your sort of final gadget out here. And what that means is that every element of the geometric algebra is going to be a sum of the scalar part and the vector part and the bivector part and the trivector part and yada yada yada. That's what those are some of the basic operations. Again, the idea is that you know, if you want to get some more geometric intuition, I heartily recommend you know, some of these YouTube videos to kind of give you the geometric intuition. But let me stop here and just see if there are any questions so far.
So you mentioned when you have 2 e's, this is not like just a line, right? It's you mentioned this is like,
so this thing here is to be thought of as the geometric product of E1 and E2, right? So if I have, let me try to give you a picture of this. Okay, so Go here. What? Why did that happen? Oh, I'm not interested in that. There we go. Okay. Okay, so suppose I have, a vector that's, like that, and then another vector, which I'll rotate 90 degrees, about like that, and then move it down. Okay, so there's a couple of orthonormal vectors. So then I'm going to think of this thing here as defined by this space. Together with an orientation. So there's an orientation. See if I can draw that using OmniGraph. I'll give it a whirl. Here we go. Let's try this one. Come on.
So are you saying that you're adding like parallel vector to both of these E1 and E2?
What I'm saying is that it's this area.
Mm-hmm.
So it's not your usual thing here. It's really an area, right? So it's a different kind of gadget. That's close enough. All right, so you can see that's the orientation, right? So it's this area together with this orientation. I mean, it might be helpful if I go ahead and connect them up, so you see what I mean.
Can you explain why is this orientation?
You need this extra piece of information to make all of the product stuff work out, right? Because you have this anti-commutativity. So you need the extra information to make the anti-commutativity of the geometric product work out. So the orientation is carrying that information.
Oh, so you're saying it's not important left and right, but we just need to be consistent for every terms.
That's correct. Yeah.
All terms. Okay.
Yeah, exactly. Yeah. So if this is E1 and this is E2, right? Then this thing here is E1, E2.
Okay.
So hopefully that makes some sense.
And how we were representing E1, you didn't say that, right?
So E1 is like E1, E2, E3 can be thought of as basis vectors for R3 in this example.
Okay.
Right. So this vector here is E1. This vector here is E2. Right. And then this thing here is the geometric product of E1 and E2. So what that means is that in general, we also have this notion of grade, right? So we can take an A sure, what have I got? Do I have brackets? I do not have brackets. Okay, I'll just do it. So we have, oh, that's not so good. Let's see, parentheses. Huh. All right. So we have that one and that one. And so if I then if I use R for the rank, okay, so then this is just going to be the rth, right? So if the vectors is really, if the element of the algebra is really like this, then this is going to be the rth component, right? So so this will be using this notation here. So let's say I just used A instead of A, B, and C, right? So this would be A11, A12, A13. This would be A21, A22, and so on, right? So this would be the the rth, so the A sub R, and then you need all of there'll be what, n minus R of them, right? But I think you get the, and then this will be E1 through ER. So I think you get the picture, right? So you'll have to sum over all of those, but right. So you'll have to, in the same way that, when you're looking at two, you have take any two out of three, or take two out of if you have an n-dimensional space, right? Then maybe take 2 out of n, and for the rth it would be take R out of n, right? So this is going to be some sum. So hopefully that's clear enough. You understand what I'm saying. Does that make sense? Like, so when R is 2, right, this would be B1, E1, E2 plus B2, right? It's all the two components summed together. When it's in general R, it's the rth component of this sum, right? And so in particular, 0 is just going to be the scalar part, right? It's just the scalar part, right? So
this is like
I wrote this as A0.
So if this is like a big sum type, we want to take from each possible case, we want to take a specific, I'm not sure how to say, specific
Component.
vector, or
It's a component. Yeah. And it won't be, right? So this is a scalar, that's a vector, this is a bivector, this is a trivector, and in general you have an n vector, right? And so the reason I mention this is because I want to point out something, right? That when you take the geometric product, you get something of grade 0 together with something of grade 2. Right, so this grade goes up. So this is a grade increasing gadget. All right, so in the case of the three space, when I take the geometric product, I'm getting a scalar plus a wedge, which is a grade 2 gadget. All right, and you can see that because this is grade 2, right? I have grade 2, this is grade 2, and this is basically, you know, it's just a scalar. I mean, it's a sum of grade 2 gadgets. So this is grade 2, this is grade 0. So when you take a geometric product, you're actually going, you know, you're modifying the grade. So these operations can change the grade of the gadget that you've got. And that's something that's interesting and unique about Clifford algebras. So in general, what we can say, you know, now that we've sort of discussed this a little bit, right, we can say that there's a kind of representation for every element, in the sense that A is equal to the sum right, like that. So if you take the rth component ranging from 0 to n, where n is the size of your space, right, then A is always just the sum of those components. Does that make sense?
I think yes. Size of the space is the biggest R, right?
Yeah, or I'm saying n is your yeah, n is the size of your space. So this sum ranges from 0 to n.
And the grade in relation to size of the space. I mean, like, oh, so when you say size of the space, this doesn't mean like some kind of dimension.
It is a dimension. Yeah, that's exactly right. But it's correlated to dimension, right? So notice that the number of elements here is quite a bit larger than just the 3 orthonormal basis vectors that you get for 3 space if you consider the vector space, right? The vector space, right? The number of basis elements will be equal to the dimension. And for Clifford algebra, the dimension will be smaller than the number of basis elements.
Oh, I see. And the grade is
it's
basically how
it's a way to project down to some subspace, right? Where you can have 0-dimensional spaces, which is just scalar. You can have 1-dimensional spaces, 2-dimensional spaces. So if you have an n-dimensional space, the grade allows you to pick out the subspace. So every n-dimensional gadget is the sum of all of the, you know, stop that. Is the sum of all of the m-dimensional gadgets, where m is less than n. That's the way to think about it.
So when we have 3 e's, this basically means the grade 3 we can have.
Yeah, that's right.
Okay.
That's correct. That's right. So there, you know, when you're doing 3 space, there's lots and lots of fun things you can do. So you know, hopefully we'll get into that at some point. I want to, there's some stuff I want to look into that is bothering me in a lot of these presentations, especially when you get into geometry, because they start taking exponents of gadgets. And I want to make sure that that presentation is consistent with the presentation, with the axiomatic presentation, which currently I'm a little unhappy with. But you can easily define rotation and translation, and all the usual stuff is extremely compact in this notation, which is why a lot of people prefer it. And if you look, it's been taking physics and graphics by storm for the last 10 years, because it is so much more expressive. The size of the expressions you use for Clifford algebras is way smaller than what you would do with quaternions, for example. So that's part of the reason that people are so excited about Clifford algebras, is because the algebra, even though it takes a little bit of conceptual adjustment, it gives you a very concise language for the usual kinds of things that you want to say in graphics and or physics. So again, I encourage everyone here to just go take a look at some of the geometric algebra. Is basically just Clifford algebra with an emphasis on its applications to geometry. There are other applications. For example, the R10 braid group. So Kaufman and folks show that you can find a representation of, at least a partial representation of the R10 braid group in Clifford algebras. So it's not just about geometry; it's about other things as well, right? It's just an algebra, right? So there'll be lots of models and lots of interpretations. So it's, but people have found that the geometric interpretation and its application to physics is very compelling. And we'll get to examples of that maybe next time. But okay. So the thing I'd like to focus on is that you can just incorporate Clifford into rholang, right? The whole principle of rholang is that values are processes. So for any n-dimensional Clifford space, you can literally just incorporate the space of values that's defined by these formal sums as processes. And so let me just stop there and just make sure that everyone understands that idea.
And the plus will be the power, right?
No.
Oh. Mm.
No. The point of rholang is that you can take any data type whatsoever and just incorporate it in the language, right? So all of the operations that are native to the data type are supported by the data type, right? So just like, when we incorporate numbers as processes, right? So, right? They're just numbers, and so I can write x plus y par z plus w plus z, right? And that's meaningful in rholang, right? The x plus y will be reduced to whatever that real number is, and the w plus z will be reduced to whatever that real number is, and then it'll just be a multi-set of those numbers, right? They're running in par. So you can do exactly the same thing with any data type whatsoever, right? So rholang is designed to be modular in that sense. So you can always expand the language by just adding a new native data type And the trick is that the values of that data type are processes. And since they're processes, you can send them by putting an at, right? So the general scheme is, so the general scheme is that, so given some ADT, then you can define, let's call the ADT A. Then you can always define rholang plus A as the unique extension of rholang with,
These are basically ground types, right?
they become ground types. That's right. Unique extension of rholang with values of A as processes. All right, so then the next step is, of course, that we can just do that. So example, rholang plus geometric algebra. Okay. So now the thing that I'm driving for is that there is a variant of you can so this one is obvious. Now what I'd like to do is to describe a variant which is a little less obvious, which is a new COM rule. So but we can define a variant which comes equipped with a new COM rule.
And this new COM rule is this what we want to represent for sum?
No.
Okay.
No. So the idea is that suppose that A dot B is equal to 0. That means that they're orthogonal in some sense. Yes? Does that make sense? Just like with ordinary vector spaces. Okay. Then we want that. Okay. For y from at A, P in parallel with, can you guess? What am I going to do?
Sending something on B.
Yeah, right. So then we do at B, bang Q reduces to P with at Q for Y.
So we have some kind of, we want to have geometry describing the common.
Yes, but notice that it's an active geometry, right? So the thing about vector spaces and classical mathematics in general is that there's no dynamics. The vectors don't represent the dynamics. Neither do the elements of Clifford algebra. They don't represent dynamics. They represent static information, structural information. in a vector space, the dynamics are in the transformations, right? The linear transformations or other kinds of transformations, right? That's where all the dynamics are. But in process algebras, you package the dynamics with the algebra, right? It comes with the dynamics. So that's new and unique in process algebras. So that's our additional COM rule. Now, the thing that's even more interesting is that you could imagine changing the geometric relationship. That instead of, so you start with this COM rule. So let's call this COM rule sub bottom, right, for orthogonality. Yeah.
And Greg, when you're using orthogonal or orthogonality, orthogonal, that's right angles. Is that correct? Is that
Yeah, they're perpendicular to each other. Yes.
Okay.
They're pointed off in different directions.
Now, pointed off in different directions, or are these different directions always 90 degrees? Or is that not necessary? They're just different directions.
You can think of it as 90 degrees. That's fine. It won't hurt your intuitions.
Okay.
So think of it.
In general, it used to mean that they're independent of each other, right?
That's correct.
Okay.
So what we're saying is, if they're linearly independent, but notice that you could. So this is where things start to get very interesting, and there is no process algebra that I know of that does this, but it's certainly hinted at when you start to look at some categorical semantics of process algebras. So after you've done one of these, you could imagine, for example, that you change this relationship. So you could say instead of 0, this is not the best example. I'd like to change the example even more dramatically, since we have Clifford algebras, but since we're kind of getting close to the top of the hour, I'm just gonna, let's say this is -1, right? So then, to make it easier, let's do 1. And so now you can start to see where I'm going to go, because I can do this. So let's call this sub 1, right? And you can imagine that there's 1 for 2. So now imagine that here you encapsulate this guy in a space where, so I'll use brackets again. So we're moving this one over to a space where the COM rule that's in effect, I'll just do it this way. Oops. That's not what I wanted. There we go. The COM rule that's in effect is COM1. Right? It can no longer interact with things that don't support COM1. And then this one, you could easily imagine that it goes to COM2, where COM2 is, as you can guess, this one. Does that make sense?
Are you saying that they are like tagged in some sense? Or
what I'm saying is that after once this has happened, this process is no longer subject to this condition, right? It can't, like the A and B thing has to equal 1, not 0. And then after a pair in this process has reduced using the 1 rule, they move to the 2 rule and the 3 rule. Do you understand what I'm saying?
So you're not saying that we will make the reduction. We will still have this radix.
What I'm saying
Right.
is, as long as these are in, so now what I'm suggesting, I'm trying to suggest a notation, right? So the notation is that processes come with information about what COM rules they're sensitive to. So really what we have here is some brackets around this. Okay, so
I see.
so then over here we have a bracket like this and a bracket like this, and then we're going to use the bottom. Okay, so now what we're saying is, if you found a pair in the orthogonal namespace or COM space, right? It's not really a namespace, it's a COM space, that has this relationship, then they reduce and it populates this COM space. And if in this space,
so we are looking at A and B, and we are applying some geometric rules to see if and applying geometric rules, basically we are searching for a COM rule that we can
yes,
that we can apply, and then
yes,
okay.
and now just to whet your appetite with where I'm going for this, imagine that at the time that we do this reduction, we draw a line, right, from A to B, right? They're orthogonal, so we know we can draw a line from, tip to tip, right? So I can use reductions like this to start to make drawings. And I can use changes in the COM rule to change how I draw. Does that make sense?
Yeah, and we can go backwards, right? We can have some change in geometry, and we can use this to use as a source for how for changing the COM rule, for example, right?
For example. Right. So just to be clear, to summarize, and then we'll close it out. Clifford algebra is well understood. It's like over 100 years old, and it's in the last couple of decades that people have started to realize that it's not just a nice formal system, but that this formal system has tremendous advantages in the reasoning about geometry, and therefore reasoning about physics. Then rholang, it's like getting close to 20 years old. Certainly the rho.calculus is getting close to 20 years old. So this part, adding an ADT to rholang is totally straightforward. It's just engineering. There's no innovation, right? Rholang plus geometric algebra, no innovation whatsoever. Totally well understood. Now this part is new, right? Forget about changing the COM rule. Just having the COM rule depend upon your geometry is very interesting, right? And you can have the usual COM rule plus this COM rule, right? So you have the normal thing where you've got, at P and or at R and at R, and that just does the usual things that rholang does. And then this is an extra information, right? So the rholang engine has to go and check to see, you know, all right, is this a geometric algebra value? Okay, it is. Is this a geometric algebra value? Okay, it is. If I you know, dot them together, do I get 0? I do. Okay, great. Now I can run the thing. So that's new. And then, but that's, you know, it's only just the beginning. Once we have this ability to add different conditions for what makes the two ends of a channel, what makes the two ends of a communication, we can start changing as we evolve what makes the two ends of a communication. So that's also very new. This part you could kind of get out of the annihilation rule, but this part here, that has not been proposed before, right? This is you're hearing it for the first time. Does that make sense?
Yeah, this is very interesting.
Yeah. So the point is that you can now start to talk about dynamics in space. Right? This gives you a way to reason about spatial dynamics, right? It's no longer about linear functions. You're using a different idea about how to do spatial dynamics. When the question is, when do two locations or physical quantities give you a notion of a channel between them? And it has to be something that you could measure or calculate effectively, right? It has to be an effective calculation, and it has to be, and as a result, it has to be, you know, objective, right? It's a property of the two physical quantities. And so that's the principle, is when can two physical entities create a channel? And you can be quite creative in that regard. Thank you very much for your time and attention. I'll see many of you in the dev stand-up in just a little bit. Ciao.
Thanks. Bye-bye.